Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a great pleasure to introduce Professor Rajiv Gupta at the University of Arizona. And Rajiv has been doing work in programming languages and architecture, power and memory embedded systems for many years now. And he's holds many patents. He's supervised 15 PhD students and received numerous awards, including a Distinguished Paper Award at ICSI, a paper in the best papers in 20 years of PLDI, et cetera. So Rajiv's also been a great contributor to the community, the programming language community, involved in many professional service activities, including program chair for PLDI 03, and he's going to be the general chair for PLDI 08. So if you have any ideas about sort of how to make that better, you can talk to him after the presentation. Yeah. Okay. So anyway, so today Rajiv is going to be talking about automated fault location using some of the program analysis he's developed.
Okay. Thanks. So the talk is about dynamic techniques for automated fault location, and the motivation for this work is clear that the presence of bugs really reduces the productivity of the developers and so on, and there are studies which show that it costs the economy, and of course in the embedded system scenario that the bugs can lead to rather disasters on missions where the whole mission can be lost because of a bug. And here I listed just some of them. So for example, here an arithmetic flow caused the shutdown of a guidance computer and caused the rocket had to be destroyed after a few seconds of launch, and there are just numerous famous examples of this sort. So what I'm going to talk about is really working on techniques which help in debugging the program. And of course, to get reliable software, there are a lot of things you have to do. One of the things is debugging. And just to define the scope of this talk, essentially our main goal is to basically, if we have a run in which the program fails, we want to narrow the fault to a small section of the code, present it to the user, so user can then examine additional dynamic information and try to figure out what went wrong. And the scope of the work is that we are trying to, our goal is basically that we want to be able to apply our techniques to long-running programs, multi-threaded programs. And so basically the dynamic information that we collect to guide this work is basically fine-grained execution traces, where you're looking at the dependencies that are being exercised, the path that is being taken, and the values that are being generated. So very fine-grained information at instruction level. And we do the analysis of a single failed execution run. And we also, in addition, will perturb the execution of that run to see how it affects the behavior of the program, and we use that information to actually guide us in finding this section of the code. And finally, to further scale the applicability of this kind of techniques, we are looking at two approaches. One is how to compress the information that is being collected, and the second is to integrate it with a checkpointing system so that we can collect the traces on demand rather than to collect everything beforehand. So okay, so basically this is just showing what a dynamic dependence graph is. So let's say I have a program, the program follows some execution path, then we build a dynamic dependence graph from there, where these nodes are just the statements that were executed, and the edges are two kinds. One which show the flow of values from the producer to consumer instructions, so those are the data dependencies. And then we have the edges which show control dependencies, which is between a predicate and the statements whose execution that predicate caused. So those are the very basic sort of dependencies that are in the graph. And our goal is that if something went wrong and we got an incorrect value, we would like the user to just focus the attention on this part of the graph, which captures the faulty code and the erroneous value. And so we would like to get as close as possible to this part. What is the overall approach? Basically, what we like to do is find some statement in this execution which is such that either the faulty code affected the value computed by S, or the faulty code is affected by the value computed by S. In other words, S is related to the faulty code through a chain of dependencies, either in the forward direction or in the backward direction. So FX means that if starting from S you go backwards through the dependence graph, you will find all those statements which influence the value at S, and hence those could potentially be faulty. And affected by means that you actually go forward from S through the graph, and you find all those statements whose execution was triggered by S, and hence the fault was triggered by S. So so this is referred to as a backward slice, this is a forward slice. And if we have many such S's, if we find many such points, we can find these slices and we can intersect them, because given a statement S, essentially we are finding a set of statements which are potentially faulty, and then the user has to examine that manually. So if we have many such statements, we can intersect the slices that we get, and we can get even a smaller part of the graph. So the traditional approach has been to always look at the erroneous value that's produced, go backwards and compute a backward slice. So this has been around for a very, very long time, since 1988, and it's been used extensively. But as I said, we want to be able to compute multiple slices and intersect them. So the second thing we looked at is that you may be able to find what is referred to as a failure-inducing input. Zeller basically proposed an automated algorithm for finding the failure-inducing input, and here the idea is that this part of the input really triggered the failure, not all of the input, but this particular part of the input. And it's easy to find if you think of it this way, that if we change this part of the input and the rest of the inputs are the same, the fault would go away, which means this input is triggering the fault. If that is the case, we can take a forward slice from there, and we get another approximation. And of course we can combine both, and we get a smaller approximation. So I deliberately drew this so we get a single sort of chain, and hopefully if it's a single chain you'll be able to look at it and understand it, assuming this chain is actually the right chain. So it's important that we capture the chain which actually conveys what's wrong with the program. Actually, for certain kinds of bug, this kind of approach is extremely effective, like you end up with only very few statements. And the typical example is like a buffer overflow type of bug, where the bad input actually caused the buffer overflow. So then what ends up happening is you have a chain from the input, the part of the input which caused the overflow, to the statement where it was read and it corrupted the memory, to the statement where the corrupted memory was accessed and your program perhaps crashed. So so basically you capture this sort of spurious dependence which is there, and you end up with very few statements. Of course, in general, doesn't mean you are going to get very few statements. Okay, so let's just move forward. So let's say I have the failure-inducing input, erroneous output. There can still be many, many chains and a big graph in between. So we look for another opportunity here, and here essentially what we are doing is something like this, that we try to locate what we refer to as a critical predicate. And the idea is that critical predicate, let's say it evaluated true during the execution. We want to flip it to false and see what its effect is on the execution. And if its effect is that essentially if your program has failed, that means some part of the state is corrupted, and that's how you got to where you are. If switching the outcome of the predicate can fix the state enough that your output, for example, becomes correct, or if you had a crash that goes away, then you can say that basically that this is actually an improvement over the run that you had. And actually all we want to say is that this predicate is somehow related to the fault through dependencies. And in fact, what we can say is that something like this: if from the predicate we should take the backward slice, because maybe this was the faulty statement, and due to this statement the predicate went the wrong way. Or it can be forward, because it's possible that when you made the predicate go the other way, you avoided the execution of the faulty code, and therefore the program seems to behave better. Not perfectly, but better than before. So maybe you avoided the crash, but the program is still not correct. So you really need to go in both directions and capture this kind of slice. And of course it's a bidirectional slice because you're going in both directions. And now if you intersect it with the previous one, you will prune out more chains, and maybe you get again a smaller slice. So the key thing here is, how do we find out these critical predicates? Actually, they may not always exist, because your bug may be so complicated that you need simply switching one predicate doesn't have any effect on your program execution, significant effect on improving the program execution. So in other words, you really need to make a lot more changes to the run to achieve anything good. So for the small number of bugs we looked at, we were able to find the critical predicates in bunch of them. And how do we find it? Basically, you start from the end and you go backwards, and you try these predicates one at a time till you see one that is that's a critical predicate. And if you do that carefully, in the sense that you filter out sort of unnecessary predicates, you take a backward slice and you only look at the predicates which are in the backward slice, and then you order them based on going backwards, you end up actually looking at far fewer predicates. So in a very sort of reasonable amount of time, after trying reasonable number of predicates, you are able to find a critical predicate.
I missed it, Rajiv. I'm sorry. So do you re-execute?
Yeah, we re-execute. So essentially you're re-executing the program and stopping the program at that predicate and forcing the execution in the other direction.
So it's like a fault injection. You just
exactly, yeah.
You just make the predicate
go the other way, yeah. So
you haven't run into problems where doing that causes some other inconsistency or bug, aside from the one you were just looking at?
Oh, so basically that's why we may not always find something. So if we get something which seems okay, we take it, but it doesn't mean that every time you switch you get something meaningful.
So like in Zeller's framework, you repeat the result, you don't get the result, or you get something else.
Something else, yeah.
You just sort of say, I'm not interested.
Not interested. So that's what you're doing. You're searching till you find something interesting, and then you stop and you use it. And in fact, actually in some cases we've also seen that you may find a critical predicate, and it may even fix the program, but it's not the one you want, because...
Right, so when you say repair, in some sense, do you mean just it goes to the end of execution with no observed error?
Yeah,
is that
exactly. Or actually, so if it's producing an output that was wrong and it corrected it, then of course it's clear. But in case of a crash, what we are saying is if we went to the same part of the code, but this time without crashing went through it, we say this is good enough.
And there wasn't another crash later.
Yeah, well, we just stop there. If we go to the crash and we went past that, we say this had some positive effect, but we don't necessarily go all the way to the end. So the thing with this is that, so what I was saying earlier was that actually it's possible that there are many such predicates, but they're not all equally meaningful. In other words, when the user looks at them, some of them will be very convoluted. They may have a good effect, but they could be convoluted. We didn't see many such cases, but there was one case where the first predicate we looked at, critical predicate, was not good. If we searched some more, we found another one, and then we were able to actually understand what was going on with the bug. So let's say we have done all that, we have intersected them and gotten something. So this one more idea is something like this, that let's say you have a program which is producing some correct results as well as wrong results. So here, can we infer something from the correct results? Can we use that to further prune the graph that we are left with? So the idea here is that if you have some value that this statement produced, and it was used both in computing the correct and the wrong value, what can you say about this value? In the sense, is it correct? Is it more likely correct than wrong? And so we apply a very simple sort of intuitive idea, and the idea is something like this, that we'll associate a confidence to this value between 0 and 1, and 1 means that any change in the value will change the correct output, which means you need exactly this value to get the correct output. If you change it anyway, the correct ones will change, which means that you can say I have a very high confidence that this is probably correct because it's producing the correct value. But on the other hand, if changing the value v doesn't really affect the correct values, that means we can't say anything about it. We can't say it's right, we can't say it's wrong, so we have sort of zero confidence in it. So we apply that kind of approach, and so for example here I'm just trying to show that this is correct, and somehow you infer that we have very high confidence in these values. Then we will filter them out of that chain and we'll get a smaller chain. And we found this to be effective in reducing the size of the chains. So we applied these techniques to some bugs that we had collected off other research groups and websites and so forth. And so there are two types, some which produce incorrect output and some where the program crashes. And then this is basically a suite of small programs where the reason for using it is there are a lot of test cases, a lot of faulty versions and so forth. So we use that. And if you look at the various kind of slices, backward, forward, and bidirectional, so you see in these programs that their sizes vary. So there's no one winner that you can pick one and say I'll forget about the other ones. So here, like, this is the smallest, here this is the smallest, here this is the smallest, and so on. So there is some merit to using multiple slices. Basically, that's what this says. And then sometimes all of them may not be applicable. I already mentioned you may not always find a critical predicate, in which case you don't have a bidirectional slice. But also, like, even a backward slice. So for example, here there were some bugs where because of the bug there is no output generated, because it's doing matching and it doesn't find the match. So since we were starting from the wrong output, if there is an output, the wrong output is useful. You can start from there. If there is no output, then you don't have a starting point to do the backward slice. So if we combine all of them, then this is what we end up with. And you'll see in some cases we are actually ending up with very small number of statements compared to the backward slice, which was the traditional sort of approach. Okay, so this is the pruning experiment, and as I said, these experiments are based on the Siemens suite, where we took some versions of the program which had faults injected in them and some runs for which we were given the inputs. And here what we saw was that, so these were the backward slices, and after pruning these backward slices, this is what we got. So in some cases, of course, we get dramatic reduction. In other cases, the reduction is less. But again, I mean, if you can combine all these techniques, that is the reason to have many such techniques, because no one would be perfect for necessarily every program. So these are the two where the reductions were the most. So the summary is something like this, that when we did backward slices for these programs, we got like 31% of the executed statements in the backward slice. When we intersected the various slices I was talking about, we got 36% of that. So it was like 11% of the executed statements. And when we applied the confidence analysis and pruned the backward slice, we got something like 13% of the executed statements. So these techniques, I mean, once you go beyond one type of slice, I think then the potential is there to reduce this. And obviously, I mean, the ideas I mentioned, I mean, failure-inducing input has been around there. Switching the branch is something we tried. Obviously, there could be other ways you could identify such statements and compute slices and potentially reduce the search further. But these are the ones we have come up with. Yeah.
So do you know what the percentages are for the static projection of the execution onto the static program?
Oh, so actually this is, when I say 31% of the executed statements, it's like the 31% of the static statements which were executed.
Okay.
You know what I'm saying? So it's not the instances, it is actually, we mapped it back to the source level statements, and then you count the number of lines, number of source level statements. Yeah. So basically, all the data is in terms of the static number of statements. But of course, we have the graph. If the user wants to see it, they can look at the graph and so forth.
But still, if in a really large programming, if the universe of executed statements is 100,000, it still
could be larger. Yeah. So in these ones, I guess this is the type of bugs. The number of executed statements were really not very large percentage of the static statements,
Right.
and so that's why the numbers were so small when I showed you in the previous slide. So I guess because many of them crashed and they didn't go very far before they crashed, that sort of thing. Yeah, so this is, that's why, this is not enough, but the point is it's automated. So if you can come up with additional ideas like this, and you can essentially you're putting your program through many filters, and if you can come up with sort of orthogonal ways of getting these statements, you hopefully will be able to reduce it further.
And this should work with any kind of bug oracle, not necessarily a crash. Like if I have some dynamic analysis on the side that tells me this is a bug, I can catch it earlier and I should get this.
Yeah, it's not really exploiting anything it's not doing anything special for special kind of bugs. It's very sort of generic technique in that sense. Yeah. Okay, so I want to mention this briefly, but we just worked on this. So there is sometimes what happens is that so far the assumption was that you're going to generate these slices, and slices will capture the faulty code. So you intersect it and you get the faulty code. But sometimes it's possible that the faulty code is not in the slice, and this is a trivial example which shows that. So let's say there's a problem with this statement, it causes the branch to go this way. But the branch should have gone that way. Now, if it went this way, what is going to happen is, and later on you see that this value is wrong and now you're slicing on x. So what is going to happen is, if you look at the dependence graph, this value of x is coming from here. There's nothing wrong with these statements. What's wrong is actually here. But this is not really connected to that. And so the problem here is that this statement was never executed, and hence no dependence was created between this and this. So for this, again, you need to figure out that you need this additional dependence between this statement and the predicate, and you can figure out again by switching the branch, because you can go back. So for example, you can say for this predicate, so basically first you apply the previous techniques. If you can't find anything meaningful, you're saying expand this further. And when you expand this further, essentially what you will do is you'll pick one predicate at a time, like you pick this predicate and you force its execution on the other side. If it goes on the other side and you get a different value of x here, that tells you that this predicate is relevant. And then if it's relevant, you will introduce this dependence. You'll introduce this dynamic dependence. So we're just calling it implicit because it wasn't one of the explicit dependencies that we captured before. And so the basic idea here is you look at the slice that you got before. If it doesn't help, then you expand it one predicate at a time and see what happens. And the small number of cases where we had these kind of bugs, when we applied it, usually we had to expand the slice very little to get the faulty code into the slice. Like one or two predicates we expand and we capture the code. Okay, so now I'm going to switch a little bit and just talk about what kind of information we were collecting, how we were saving it, and then so hopefully it can scale to larger programs. So the first thing we tried was we just collected. We know what information we want: dynamic dependencies, the values for pruning, and we collect this information. We annotate our program with this dynamic information, and then we can do all the analysis that we want to. If we just blindly capture this information, we are collecting a lot of information for every instruction, because we not only we know all the operand values, the result values, the dependencies. Essentially, we have where all the functional execution of the program captured there. So first, what we tried was to just compress this information that we are collecting to see how much we can collect. And so idea there was that if we capture the dynamic control flow, and dynamic control flow, we know how to compress Jim and Tom, and a lot of people have done a lot of work in this area. So we are just leveraging off that, and we are saying that, you see, if you capture the dynamic control flow, you can infer a lot of the data dependencies. And the ones that you can't infer, like through memory, you really need to capture explicitly. So it turns out that those are very few in number compared to all the dependencies, because the rest of them you can just, if you know the control flow, you define this register and you're using that register there, so it must be the same value. So that's the basic approach we use there. And of course, for values and addresses, again, there are various prediction-based methods to compress, so you can compress them using that. So the representation looks something like this. Let's say this is our program. We execute it on some input. These are the statements that are executed, and these are the various data dependency and control dependency edges. The way we'll represent this is we will just assign a number to each of them, and then we'll annotate the program with these numbers. So if we annotate this program with these numbers, it captures the control flow, and then we can represent dependencies by just saying what pairs of instances of the statements were actually involved in a dependence. So now you have the dynamic graph actually captured in this labeled information. So similarly for control dependency, because each pair tells you which instance of which predicate controls the execution of its statement, and so on. And actually, you really don't have to capture all of them, because, as I was saying, that many of them can be inferred very easily. So for example, if you have something like this, you compute x, you use x, and you know that this x always comes from there is no point capturing all these dependencies. You just need to, so some of these edges you can make static. It's only the other dynamic edges for which you don't know where it's going to come from, you need to capture all the instance information. So like if I'm traversing this graph starting from here to here, in between I have this edge because this could have come from different places. So I have this edge. Once I get here, I just follow this edge, and then I follow that edge. So main thing is that for all of the instructions, or all of the dependencies, you don't really need to explicitly capture them, because you can infer them. And let's say you have this situation where there was some pointer access here, so this sometimes depends upon this and sometimes upon that. Now, of course, it seems you need to know when it depended upon this and when it depended upon that. But even that you can reduce if you do the following. You make like 2 copies of this, and you dedicate the 2 copies so that, if you come this way, it corresponds to this case. If you go that way, it corresponds to that case. So it's like just what we do in optimization, specialize the code. You're just specializing the graph, so you don't have to capture all the instances. You just create 2 copies, and then now you can throw away all this information, which may have many, many, many instances. So the other thing is that having done this, that if it's local and the dependency is fixed, we have a way of optimizing it. Why not actually change the program? So create traces or paths, and take those paths and use them in the representation, because then more and more of these cross basic block dependencies will become local, and then we can apply the previous 2 steps that I mentioned.
So that transformation was based on lifting some code to know that you would take that trace? 3, 4, 6, 7.
Yeah. So basically, what you would do is you would separate this out, which means at runtime you'll have to say, if I follow this one, if I follow this path, I'm going to label this particular node. But if I don't follow this path, then I'm going to label along those.
I'm just missing something. How do you know at 2? Which of 3 ways?
Oh no, this is not an executable representation. This is just for representing the trace. So you can, it's like just saying, instead of this graph, I'll create this graph, and they both capture the same information, but it's not really executable.
So are you saying it's the post-mortem analysis?
Yeah, you can do it post-mortem, or you can do it like this. You can detect these at runtime and create some additional nodes, so later on the trace would get compressed. You know what I'm saying? Or you could do it, if you had like path profiles, you could use them to first restructure your graph and then do it. So all those are fine. Actually, we have tried all those options at various times. So the other things you can do is, for example, actually this is more for control dependencies, even though here is shown with data dependencies. If there are many edges which always have the same labels because they follow kind of the same behavior, if you go from here to here, you have this dependency. So then you can basically create one edge for these so that you don't have to replicate this information. And this happens with control dependencies very often, because one predicate may control the execution of many statements. There's no point having multiple instances of control dependencies for all of them. So you can do this kind of sort of grouping or sharing the instances. So anyway, you do all this kind of stuff, and once we have done that, we end up with something like 4 bits per instruction is the final final outcome of capturing all the information we have talked about. So okay, so this is just saying what was the effect of what optimization. So infer means that you can infer them, so you don't have to capture them. And transform means if you transform, like for example creating those paths and so on, then you can infer them, and hence you don't have to capture them. So that's what I showed to you. It gets most of it, and a little bit by this grouping. And then so really you are, this bottom part is what you're really explicitly capturing. You couldn't do anything about it. You're capturing it and remembering it explicitly. If we do slicing on this final representation that we have, usually the slices can be done reasonably fast, in the sense that this is just showing that every so often, like every 10 million or 8 million instructions, we computed a bunch of slices to see how long it took. And the slicing requests were just like arbitrary. We took 25 latest loads that we executed, and we sliced on them, and then we averaged.
So is this online or offline? I'm sorry.
Okay, so the slicing is done. So this is just the slicing time. So this has nothing to do with generating the graph time. So once you have the graph and you have the compressed representation, to traverse it and compute the slice on that compressed representation took this much time. And
So when you say statements executed in the bottom, statements executed to create the graph, but the graph is not necessarily order size of the number of statements, is it? I mean,
it's not. It depends on the compression because yeah.
So so I just don't remember in the work how like are you compressing instances together, or
Yeah.
are you keeping? I mean, what form of dynamic dependence graph is it? Do you collapse all dynamic instances, or do you keep?
Oh no! It's like you can go through and regenerate.
So it's faithful. It's totally
It's
faithful
100%.
to the actual dynamic dependencies.
Yeah. So that's why I was saying what we're doing is we are getting rid of redundancy means you can regenerate that information, so you
Yes,
don't need to
okay.
keep. Yeah. So everything is there, so you can perfectly know what value was used, where the dependence came from for an instruction. So the graph is truly the dynamic graph. Okay, so so now
So all the stuff you're doing is lossless.
Lossless, yeah, because the problem is that let's say you were like there was one spurious dependency you were looking for. So I mean, doing lossy stuff is kind of hard, at least
Sure.
because if you throw out 1% of information, but that 1% includes all the good stuff, and you give somebody the remaining, it's a problem. Okay, so what we are working now is how to speed up the generation of these graphs. So now I'm just talking about the data dependence graph here. And so if we just collect all the address traces and control flow traces, it would take a long time for us to actually process it and generate the graph. Once we had the graph, then we could do slicing very fast because the way it was represented, but generation was taking a long time. So we're trying to see if we can do some online techniques, faster techniques to improve this. So we implemented essentially an information flow type situation where, because dependencies, dynamic data dependencies are just information flow. That's all it is. So we implemented that I think this was implemented in PIN. This is a slowdown. Then we started doing some of these basic block and trace optimization that I just described earlier in that context. And it reduced the slowdown. And then the latest one we have tried is something like this, that on a 2-core system, we read in the binary, then we dynamically translate that binary and create another thread. So that the two threads which are running on 2 different cores, and one thread is just doing the information flow tracking. The other thread is executing the application and shipping information to the other thread so it can actually follow the control flow and so forth. And so here there's a system from Intel called DBT. So that's what we use to implement this. So these numbers are not 100% comparable because they're from different systems, and some systems do one thing good and some other thing good. Anyway, so this is one thing we are doing now. The other thing we are doing is that a lot of this graph was useless. So for example, when we intersected, we threw away parts of the graph. If we could do that online, we wouldn't even collect the part of the graph that we are now going to use. So we are following sort of that direction. So for example, forward slicing fits perfectly with the information flow scenario because you just need to track that this part of the graph I don't need to save and this part of the graph I need to save, because this part of the graph is influenced by some input and this part of the graph is not influenced by those inputs. So you can do that. The other thing you can do is the user can perhaps say where the detailed traces are needed. Okay, so what you would do is basically for some functions you would collect the graph. For other functions you wouldn't collect the graph in detail. You will still propagate faithfully through the function so you don't lose precision, because we want to be able to report a accurate graph, but you wouldn't really save the graph. So if later on user wants to look at the graph inside that function, they can't see it, but they know that its effects have been taken into account in building the rest of the graph. And finally, this is another thing we are exploring now, that is how to integrate this with a checkpointing and replay kind of system. And here the idea is the following, that initially we don't collect the trace, we just collect an event log. So so basically when the program crashes or something goes wrong, now we can go back and replay the execution. But during this replay is when we will actually collect the trace. So it's like the second run we are collecting the trace. And now we don't want to collect the entire trace, but we want to collect the trace of the part which we think is relevant. And so what we do is basically, you can think of it as a higher level slice of the event log, which tells you which part is relevant, which part is not relevant, and then on the relevant part you will actually turn on tracing and collect the information. So so you're basically taking this log and reducing the log or reducing the execution and saying this part of the execution is really interesting, just trace this. And this can have, it's one consequence is now we can handle multi-thread programs because we have integrated it. And the other thing is, so basically its effects are something like this, that if you have multiple threads and they are just, for example, threads for user requests, some of them have nothing to do with your error, you will be able to filter them out. But even besides that, essentially what you're doing is you're trying to figure out which threads you want to trace, which you don't want to trace. So even if you replace some threads, you won't actually trace them. So for example, if you're interested in thread A, but it was created by thread B, you will run thread B. So it would create thread A, but you won't trace the first thread. You're just doing it, to do the execution. So by doing that, you can reduce this. However, there is one problem. I mean, you can do slicing on events, on files, because this information is captured in the log. But one problem is the shared memory dependencies. Those are the ones, that we want to find. Those are the ones for which we need to replay. But if to figure out what need to trace, if you first need to find the shared memory dependencies, like chicken and egg problem. First you find all of them, then you know which ones are useless and you can throw them away. But you've already spent the time. So we came up with a sort of simple dynamic technique where we divide the memory into regions, so we are not tracking per address information about which thread wrote where per address till we figure out that some part of the memory is really shared. Then we do the detailed tracking. Then other thing we can do is like if you can do simple optimizations on this, that if repeatedly the same thread is referencing the same memory, you don't have to go and check all the time that and update all the history, because it's not going to change anything. Only when a different thread accesses the same location, now it's potentially shared location. So we apply those techniques and it reduces the time and time by half. I mean, it's still very slow, but time by half, and the space because of the memory regions significantly for running this phase. Once you have this, now you have sort of this high-level graph based on which you can figure out what do I need to collect. And so we again, these are some programs which are from other researchers or from websites with some bugs, and we reproduce these bugs. And then it's something like this, that if for example in these bugs, if the program, the run that we took, these were the number of dynamic dependencies that were actually exercised during that run. If we only focus on the part which is relevant, the number of dependencies reduces to that much. But that's because, in many of them, like let's say you had 10 threads and 8 were totally irrelevant, and a couple of them were important, and then one thread was really need to be traced. And of course, so it's a function of the type of programs also. But obviously, this optimization is only possible if the program allows it. It's not supposed to apply to every program always. In terms of timing, it's something like this. So these were the lengths of the original runs. And when we did it with logging, these were the times. So it was cheaper than tracing for most programs. Here, of course, it's high. I think what we know about these is that the I/O there's a lot of I/O going on, and the checkpointing is not, the library we are using is not very optimized for that. And so basically, so this is the overhead you're paying when you're running the program. Sort of upfront you're paying this price. And then what happens is once we figure out which part is relevant, and we just run that to collect the trace, then it's very small execution time because you're running very small part of it, or you're tracing very small part of the execution. So really the price you're paying is over here, and then you're paying the price for figuring out which part is relevant, and then you're running it to collect the trace. So the system we have looks something like this. Actually, it's not like this, but it just shows the various components because it's like in pieces and lots of pieces and multiple versions of pieces. But the basic thing is something like this. We're using this Diablo for doing some minimal static. If we need to collect any static information from a binary, we collect it from there. our initial implementation for doing all the slicing and the predicate switching that I was describing and so forth was done using Valgrind because it was easy to get started and get going and get something working. Then of course this is a module which is hooked up to this, which we developed, where we are actually computing the slices and we are collecting the information and compressing the information. And this is the library that we are using for doing the checkpointing stuff. And actually, so this is where now we are using different tools so that we can do more things online and speed them up. Anyway, so that's where we are. So hopefully we'll be able to speed up the tracing even more by using some of these parallel techniques. The numbers I mentioned for the dual core was just one experiment we did now. It's in very initial stages. Yeah. So that's it.
So in some cases you had like factors of 10 or 15 for the logging, and in other cases just 10%. I mean, why such a wide range?
I don't know. I mean, the only thing we have been able to figure out now is because it's not our library, so we didn't really develop it. But it seems like when it's very I/O intensive, it's very slow. And if you're using a lot of files and you are writing and reading, and then it just keeps logging those files, and it becomes really slow. I don't know about checkpointing well enough that whether that is something that it's an artifact of the library, or whether there is something fundamental there that it cannot be improved. So we need to understand how other systems do it and so on before we know whether that can be fixed or not.
Is the internal tool here that we have that's IDNA or whatever?
Oh, I see.
That does the logging, essentially optimized logging. I mean, it has pretty high overheads. It's not 10% by any means.
Oh, sure.
Almost never.
Yeah. So this is, it's still pretty good, this library, because one person wrote it. So I think you have to give him credit for that. Somebody from HP wrote it, and it's very easy to use. It's user level. And one of the things we have noticed is basically, one of the things we ran into is that he didn't implement all the synchronizations and all the various kinds of thread synchronization things. So we had to do some work for that. But still, it was very good in the sense it was robust, and enough was implemented that we could look at it and just implement some other calls which were missing. But otherwise, it's very easy to use. Yeah.
You looked at the work they did on the cutting bots, where they sort of put a machine up and they wait for something to come and infect it, and they try to do instrumentation. It just strikes me this would be very applicable there, because then you could very easily localize the piece of the code that was exercised by the worm or whatever it is in the wild.
Yeah, sure. Actually, I haven't looked at it, but I should, I guess. Yeah. Maybe you can give me
I'd be happy to give you some pointers.
Pointers.
Is there a counterpart of this type of research where you ask the programmer for more help in discovering these dependencies?
Yeah, sure.
And maybe it's the inference problem is therefore easier, or some of the inference problems are easier?
Well, actually, at least in this context, definitely the programmer can help. Like, for example, we tried some experiments, but we haven't done extensive work on that. When we're doing the confidence analysis, let's say you do a pruning once, okay? Then if the user could tell you about more values, like this is okay, this looks okay, then you can use that to further prune, because we just need to know what is okay. And so what we tried was in some of those cases, you get couple of inputs and very soon the thing shrinks a lot. So that means if you're actually using it, the user should have the ability to do that, because the user just says, assuming these are correct, show me what you get. Then you'll get a much smaller, it's like users exploring that graph that I gave. They don't want to explore all of it. They say, I think this is okay, this is okay, this is okay. Then we prune further. Then they look at that. If it's not okay, they can unclick on those buttons and do that. So I think user input would be very useful. And in the experiments, usually we didn't do too much of that, because how it is. If we do that, people won't believe our results. They will just say, you knew the bug, so you know which one to click and which one not to click. So it's not a real study. But definitely, ourselves, we tried that with few values, and we report of one experiment in the paper where essentially the ones we marked correct what generated automatically from a different execution where the same code was executed and it was correctly executed because the output was correct. So we use that as a hint to say, mark this correct, mark that correct. So at least we were not doing it manually. But once somebody's really using it, then you want the user the flexibility. Yeah. Okay.
Any other questions?
Okay, thanks.